Hi, everybody. This is John Handler. I'm a solutions architect with AWS. This morning, we'll be talking about integrating your DevOps tooling and Amazon Elasticsearch service. So, DevOps is actually more of a philosophy or a mindset than it is a particular tool set. And thinking back on my own history, my own past, I'll tell you a story that happened for real. I was working for a company that built a product search engine for an e-commerce site. And we had these regular events where we would do innovation on our platform. And we were all developers. I was a software engineer at that point. And in these events, we would examine our code and get in there and look at our logs and really build out a picture of how our customers were using our product. One of the things we discovered was that, in fact, a large percentage of our products were never accessed. And, we were building a search engine at the time, so storage was at a premium. And we were able to optimize our usage of the storage in our search cluster with the knowledge that we gained about how our customers were using our search solution, and so save on costs and make our product perform better. So this is kind of the driving force behind DevOps. It's kind of how DevOps came to the fore. And it makes sense. Developers are actually in there building the code. If we close the feedback loop and bring the information about how the software is performing and how people are using it, developers are in a great position to be able to improve the software and make it perform better. We have our standard DevOps cycle here. And, there's a lot of different places where your software will generate logs, your code deployment will generate logs, your configurations have to be managed. Obviously, your monitoring is going to deliver tons of logs. So as you go through the development cycle and close that loop, you're able to step in a number of different places to optimize and tune your software's performance and how your customers engage your customers better. So we're going to go through a number of examples today, and we'll see some of the ways that you can dig in and where you can bring information in from the various phases in your development cycle. I just want to say a little bit about Elasticsearch and Elasticsearch service. We have on AWS a number of managed services that aid in your DevOps process. One of those is Elasticsearch service. Elasticsearch service provides you the ability to run Elasticsearch in the AWS cloud in a fully managed way. So you're able then to bring all your data in really easily. We take care of managing and maintaining the software and hardware that constitutes your Elasticsearch cluster. For those of you who are not familiar with Elasticsearch itself, I just wanted to say a couple of words about what is Elasticsearch. So Elasticsearch comes out of the search world and in fact sits in the database world. You can think of it a lot like a database where you put in your data with some structure around it, and then you run queries to pull data out of it in response to those queries. In Elasticsearch's evolution, it really started life as a text search solution. You can think of things like Google, where you search over all of the web by entering a few words. In a very similar way, Elasticsearch allowed you to upload a set of documents or entities, and then provided you with natural language capabilities to decompose those entities, parse out the text, and get it into a format that made it easy to search and easy to add essentially a search box to your website. It does support a Boolean notion of queries, and it also, as a search engine, has a notion of relevance. So when you send a query to a search engine, you're not actually going to pull out every single possible response, but you are going to want to pull out the best responses. When I search for a web page, I want to make sure that I get the best match for the text that I put into that text box, and that should be my query response. As Elasticsearch evolved, it really evolved a tool set and ecosystem around it that supported streaming data into Elasticsearch in a very fast manner. So Logstash is an open source technology that allows you to connect to an input, perform an ETL on data as it flows through, and then deliver that, that data to Elasticsearch. So with that tool and in Elasticsearch itself, Elasticsearch supports a large volume of throughput. And that really opened up the possibilities for logs. Because if you think about it, when you have logs, one thing you want to do is be able to search them. If I have a terabyte of Apache web logs, and I know I'm getting 503s somewhere, then the easiest thing to do is throw all those log lines into a search engine, and then I can simply query for status code 503 and bring all that data out. And so that really drove a lot of usage of Elasticsearch and a lot of its popularity, that ability to throw my logs in there and find problems and fix them. At the same time, Elasticsearch and search engines supported a feature which was called faceting, now called aggregations. What aggregations do is allow you to take a search result set and then perform statistics on the values of fields. In the context of log lines, what that means is I can search my Apache web logs for a particular request, say, and then look at the status codes that I received for that request itself. And then I can get a count of those status codes, or essentially a histogram of the responses to a particular request. Now, because it's a histogram, the obvious next step is to build that into a visualization of a histogram. And Elasticsearch, again, in the ecosystem, there's a technology called Kibana. Kibana is a web client that talks to Elasticsearch, sends queries, and visualizes the results. So in my example of searching for a particular request, Kibana would automatically build me that bar chart that is the histogram of that request. And Kibana also supports a time-based notion that allows me to display that graph across time and to monitor what's going on in my hardware. So that's kind of the evolution of Elasticsearch. It's driven a lot of its popularity. It's very easy to use. I can just jump right in and get started sending my log data in there with Logstash and Kibana to visualize it. 10, 20 minutes, I can have log data up. And in a DevOps context, that makes it very attractive for me to use that to look into my software and see what's happening. The challenge with Elasticsearch is not on the getting started. The challenge with Elasticsearch is really more around scaling it. So as you send more log data into Elasticsearch and you need to scale it up, it becomes much more difficult to own and operate that Elasticsearch cluster and keep the lights on and keep it running. And this is where in AWS, Amazon Elasticsearch Service steps in and takes over a lot of the operational and other challenges with running Elasticsearch. So Elasticsearch Service, as I said, is a fully managed service that allows you to run Elasticsearch in the cloud. First, most important thing, we do support the open source APIs and tools. So when you use Amazon Elasticsearch Service, you are using vanilla Elasticsearch, and you can use the tools like Logstash and Kibana in the same way that you're using them in your own environments. Second of all, we do make it easier to use Elasticsearch. With an API call, you are able to create an Elasticsearch cluster, and we spin it up, and we do all of the configuration and management to bring that cluster and make it a cluster and make it available to you. We make it easy to scale your cluster. So again, with an API call, you can simply decide to move from a particular configuration in terms of a cluster of instances to a different one. We do all the work of changing over the instances and do that behind load balancing while the cluster itself remains up and available. We have a number of security features. These allow you to secure access to your Amazon Elasticsearch cluster and to a particular granularity, control who can do what on that cluster. We have high availability features that make it easy to make your cluster more available and protect you in the case of losses of instances or even availability zones. And finally, we have a number of integrations with other AWS services. We'll go into detail on that. Just to give you a visual and a little bit of a sort of teaser in terms of what you can do with Elasticsearch. Again, Elasticsearch service provides a Kibana in the service that you can run to visualize the data in your log lines. And as you look at your logs, you can build these visualizations. You can monitor what's going on. You can look at timing information. You can look at error information. You can look at engagement information. This particular Kibana dashboard is looking at Apache web logs, traffic flowing through. So we see the number of requests that are coming through. We have some aggregate statistics. We have a pie chart that shows us what URLs our customers are hitting. We have even a bar chart of errors, as I said. And this is, an example of the way that you can take your log data and visualize what's in it. This is an Apache web log, but this would equally hold for, say, a front-end log where you logged things like timing for different calls or different phases in the processing of your request. When you use Amazon Elasticsearch service, you deploy what we call an Elasticsearch service domain. Domain is a group term that wraps all the hardware and software that delivers Elasticsearch to you in the AWS cloud. Now, as we mentioned, Elasticsearch is a clustered distributed solution. You deploy that domain using the console, SDK, CLI, or even CloudFormation. And again, that sends that API call to the service. We go off and we create all of the resources and present them to you through a DNS entry, which you resolve to an IP address to talk to your cluster. We have load balancing in front of the cluster instances, and we have two different instance types that we support within a service. There are data instances and master instances. Data instances hold the data and indexes for your Elasticsearch service, for your Elasticsearch indexes. And the master nodes are orchestrators that keep the cluster together and provide additional stability. In addition, we send metric information to CloudWatch about the cluster's performance that you can alarm on, and that gives you a picture into how you need to scale your cluster. And then we also provide audit trail information to CloudTrail. I'm not going to say much more about Amazon Elasticsearch service. I have a prior webinar that I delivered that covers the service features in a great deal of detail. I encourage you to check that out. I'll leave that on the screen for a couple of seconds here, just so you can quick copy down that URL. I will mention one thing that was a recent launch. We do have within the service a security model, which is a very layered security model. Ultimately, most of the access control provided for Elasticsearch service is delivered through IAM. Now, you can also, in front of IAM, use your VPC. So you can deploy an Elasticsearch service domain into your VPC. The DNS entry that we provide you would then resolve to the IP space of your VPC, or you can have a public endpoint where the DNS entry would resolve to an address in the public internet. But in front of that, and recently we've launched support for Amazon Cognito. With Amazon Cognito, you set up your user and identity pools. You can load in data from your federated identity provider into Cognito, and then through your user pool, you can actually specify IAM policies for different groups of users, apply those to authenticated users for use in Amazon Elasticsearch service. We support this Cognito integration with a Kibana sign-in panel. So within the service, if you use the service-provided Kibana, you would be presented then with a login dialog, and your users can log in, and they would get the roles that you assign to them within Cognito. All right, so let's dig a little bit into DevOps architectures and talk about how you would use Elasticsearch in a DevOps scenario. So let's dig in a little bit to monitoring CloudFormation for startups. So CloudFormation is one of the ways that you're going to deploy your software onto AWS. In that process, CloudFormation allows you to run commands during initialization, and you may also have additional commands or scripts that you run during that initialization period. What's difficult is eventually to go back to the instance and find all that log data. I can't tell you how many hours I've spent grepping around in the various log files under var log. So what you can do here is you can deploy the CloudWatch agent to pull that log data, things like cloudinit.log, cloudinitoutput.log, et cetera, and even your own log data, pull that and push it into CloudWatch. And then we do have a console level integration that will enable you to push that log data into Elasticsearch. The benefit here is, number one, then you don't have to jump onto many different instances and find out what's going on. And number two, you have a search engine, and all of your log data in one place. So you can treat your logs almost like you would treat a Google, where you can just dig in, run some queries, find some errors, and zero in on what is the issue and correct it. So AWS has a number of different services that provide you with continuous integration and continuous deployment. We're not going to cover all of them, but we will cover, again, one of them, CodeDeploy. Now, I'll just say there's code pipeline. Let's start with code commit that allows you to upload your code into a Git repository, code build that allows you to build that Git repository, and code deploy, which we're looking at, which allows you to push that out into EC2. In addition, we have code pipeline. This organizes all of these other services and allows you to orchestrate running them. Now, with CodeDeploy, CodeDeploy will forward its logs into CloudWatch. And again, this is going to start to become a common pattern. As you push that data into CloudWatch, or as actually CodeDeploy pushes that data into CloudWatch, you can then forward it to Elasticsearch, again, to look for issues, perhaps do some timing. So looking at end-to-end, how long is it taking? Perhaps, again, to zero in and fix something that's not going right. I wanted to say a little bit about microservices architectures, and we have a couple of different use cases here. One of these is where you're using Amazon ECS or EKS in order to deploy your containers. In this case, ECS itself sends data to CloudTrail. That data you want to be able to search. On the right side here, I have an ingest pipeline because there's a couple of different ways to get that data into Elasticsearch. In addition, you also want to monitor what's going on in the containers themselves. So most of our customers, many of our customers are using FluentD to take the Docker logs and push them out into Elasticsearch so that you can see at a container and a task level what's happening with your software. Now, I have two different paths through the ingest pipeline here. One of these is supported where you have Elasticsearch service deployed with a public endpoint. That's the Kinesis Firehose path. And one is for when Elasticsearch service is deployed into your VPC. That's the top path. So let's talk about the VPC deployment for a second. With with your VPC deployment, you want to take your data out of CloudTrail and push it into some kind of queuing mechanism. Depends a little bit on scale. If you have a large scale deployment with lots of different log streams, like ultimately you want to get those all together and push them into Elasticsearch service as a bulk, as a batch, right? So that queuing mechanism there is potentially SQS, could also be Redis, as we'll see in a second. That queue, then you'll pass through Logstash in an auto-scaled group. So you're running Logstash on EC2 instances in an auto-scaled group that's pulling data out of that queue and doing a transformation, pushing into Elasticsearch. Now, the other path I want to talk about here is where you're running Docker or on your own EC2 instances. In this case, again, we have the container and what's going on in the container probably pushing out to Fluentd. That's the usual path to take. In addition, on the instance itself, you can run an open source technology called Beats, and in particular, there's one called FileBeat that tails log files and forwards them. With FileBeat, you also have the ability to augment the container logs with additional metadata that will tell you the task in the container and enable you to push that in and dig in Elasticsearch based on container task, et cetera. And here we have, again, the same bifurcated path for getting data into Elasticsearch. Kinesis Firehose, great solution if you have a public endpoint. And then if you're in VPC, then you're going to go through, in this case, Redis. Redis serving here as a buffer or a queue, not as a cache per se. So your log lines will go into Redis, Logstash, auto-scaled, can pull that data out of there, transform and push to Elasticsearch. One more to cover is the serverless application. So in this case, we have our standard serverless kind of architecture here, Route 53 providing DNS resolution, Cognito for authentication and access control, CloudFront and S3 to provide distribution of static content, and then API Gateway to provide the application functionality itself, backing out to Lambda, and then DynamoDB serves as the repository for application data. So this is a common pattern in terms of deploying a serverless application. On the bottom, I have here, again, an ingest architecture that will take all of the data that's produced by these various front-end services and push into Elasticsearch service. Starting with CloudTrail, so we have Dynamo, Cognito, and IAM that push data into CloudTrail. That data eventually lands in S3. However, you can configure it so that CloudWatch will also pick up that data. So that's going to be the methodology there. We have, for Route 53, API Gateway, and Lambda, they push their data, their logs directly to CloudWatch. And we have CloudFront and S3 pushing log data into an S3 bucket. So we're using S3 here essentially as a data store for all of our log data. That's the collection point. And you can see where, where various services are sending data to either CloudTrail or CloudWatch, all of that data eventually will trigger in CloudWatch an event to push into S3 so that everything lands in S3. S3 is our collection point, and then we apply a very similar ingest architecture where Lambda responds to the objects landing in S3 and either pushes into that queue through Logstash to Elasticsearch or pushes to Kinesis Firehose. So one of the core questions that comes up for me when customers are doing DevOps is either they have a number of developers across their organization who are employing DevOps practices and want to do monitoring for their software, or there are a number of different pieces of software. And the question always arises, how do I put that all into one place so that I can provide a single pane of glass to be able to look into that and what are the trade-offs and breakdown of that. So we're going to spend a little bit of time here answering that question. So the first thing is, and we've seen how this looks for various architectures, but you need to build an ingest pipeline that fundamentally is going to take your data from your data source, collect it somewhere, and then provide the ability to transform and buffer that data before delivering it to Elasticsearch service. You know, in the architectures we talked about, S3 for the microservices served as that main collection point. In the code deployment CI/CD, we had CloudTrail as the collection point, with the CloudWatch as the collection point, with the CloudWatch agent serving as the collector. There are lots of different methodologies that fall in these buckets, but these are the core pieces of an ingest architecture that you need to build. And when you deliver, we're going to deliver a set of log streams that are coming from different sources. So you need to be able to send those off to Elasticsearch. And when you do that, you have a choice here. Elasticsearch works with indexes, which are the top level structure that contains your data itself. Generally, what we see, customers are using a per day index. So in this case, you know, logs-01.21/2018 contains all of my log data from that day, etc. for 122, 123, 124, etc. There's a couple of pieces of this, right? So we do this kind of data storage to facilitate lifecycle management for the data in the cluster. Generally, we see Elasticsearch is applied to a very short time frame and is focused on pulling data in real time so that you can monitor and figure out issues. So we don't see a long retention window for that data in Elasticsearch because it's a hot store. That also is one of the reasons that I used S3 as a collection point, because in this way I have the hot store Elasticsearch, which has my most recent data, and then I have S3, which contains my as long as I'd like, backwards in time, all of my data. Within Elasticsearch itself, though, again, we like to rotate these indexes and drop the oldest one at the end of a retention period. Often that looks like a week. And you know, again, your forensic analysis, your monitoring, that generally happens on a much shorter time frame. So data itself, you know, as it comes in, each of these log streams is going into an index. That index is then composed of a set of shards. Shards are the way that Elasticsearch is able to provide horizontal scale across your data set. You set the shard count when you create the index, and that shard count of primary shards determines the distribution of documents within your index across those shards. Shards do not overlap. They're each a distinct subset of all of your data. In addition to your primary shards, you also can deploy replicas. We always recommend that you use one replica. In fact, that's the default in the service, although you can change it. We always recommend one replica to provide redundancy within the cluster for your data, right? So I have a primary and a replica for each subset of the data that's coming in for a particular log stream. Elasticsearch deploys the shards elastically, that's why it's called Elasticsearch, across the instances, the data instances that you provide in the cluster. And Elasticsearch makes sure that primary and replica shards always end up on different nodes, so that if you lose an instance, you retain at least one copy of the data, and Elasticsearch then recreates the missing copy. And shards turn out to be a really important element of Elasticsearch in terms of both storage and work. So as you're creating your shards, those shards are mapped onto your data instances, and when you send an update or a query, each of the shards that are involved in that grabs a CPU and runs the request that you've sent. In addition, each of those shards then, of course, is storing the information for the set of documents that you've put in. So your primary shard count is very important because that determines the density of your data and Elasticsearch's ability to move it around, and Elasticsearch's response times and latencies in processing your requests. We recommend that you set your primary shard count based on storage with a target of 40 gigabytes per primary shard. So for example, if I have a 2 terabyte corpus, then I should set 50 primary shards. 2 terabytes divided by 40 gigabytes per shard is 50. You always want to use at least one replica for production workloads. For production workloads, you don't want to lose data, and that one replica will provide you some additional protection against that. And another key point is to set the shard count so that the number of shards on an instance is approximately equal to the number of CPUs. We're going to say a lot more about that. Finally, a best practice is to try to keep your shard sizes as close to one another as possible. If you have a cluster that's hosting multiple log streams, you want to try to set your shard counts so that everything has roughly 40 gigabytes. That means if you have a log stream that's only pushing 1 megabyte a day, you should probably not rotate that index for at least a month. So it's not wrong to have a single primary for a small index, is what I'm saying. To set your shard count, you use an Elasticsearch API. You put to your endpoint, and you can set a template which will set the shard count for any index that matches that a wildcard name, right? So when we were creating these log indexes, we had a prefix which was logs underscore. You set your template with logs underscore as a wildcard, and then you can put as the settings number of shards 50, number of replicas 1. In that case, whenever a new index is created, and depending on your ingest architecture, that will usually create the index and rotate it forward in the days. Whenever you create an index, that new index will get the shard count that you set here. So, well, let's return to the main point and talk about handling tenancy within a single Elasticsearch cluster. If you have multiple log streams that are coming into a cluster, you have 2 different paths you can take. The first of those is to host all of the different log streams within the same Elasticsearch index. The second path you could take is to create an index for each of those log streams and host each index separately. They have different characteristics and different trade-offs. So if you put all of your log streams into the same index, and then you have the scale for that index set based on the total volume of data that you're sending in, that enables you to distribute the processing more equally. Because essentially you're just dealing with one index, you can figure out exactly how that's going to spread across your instances in your cluster, and that will give you the most even distribution. On the downside is that then you have to scale based on your largest tenant. So that means if you have a log stream that's pushing a terabyte a day and another log stream that's pushing 10 gigabytes a day, you're ending up scaling based on that larger use case. That can be inefficient and can push you into scaling larger than you would if you handled those in different clusters. Another limitation is that you have a single index pattern. In Kibana, you'll have to do filtering based on a field that you add to your log streams as they're coming in order to parse and pull out that particular log stream. Not terrible, but that is different than the other use case. If you're handling each stream in its own index, then you do get a benefit where your queries now against that index don't have to be distributed across as many shards, right? Because each of the indexes that you create, you can set a shard count for that specific index. It allows you to scale based on each of the tenants. So each of the tenants then you can scale independently, and it allows you to create different index patterns in Kibana at a high level that lets you more easily control what you're doing your visualizations against or what you're searching against. To understand even at a little bit deeper level, when you have multi-tenant situations, right, what you have is a number of different log streams coming in. Each of those will have an index for, call it every day, but there'll be some rotation, but let's say it's a day. So in this case, we have 3 streams, each of which has 3 indexes, today, yesterday, and the day before, and each of those indexes will have some set of shards on it. Ultimately, those shards, Elasticsearch will distribute to instances that have to house and run the requests for those shards. So one important point to note is that for the most part, and especially in a log use case, only today's indexes are actually going to be receiving any kind of updates, and mostly today's indexes will be responding to queries. So when we think about how these shards are going to map against CPUs, for all intents and purposes, we can ignore everything but today's indexes. And then, what we want to do here is set the node count so that the shards per node is the number of indexes times the number of primaries in each of those indexes times how many replicas we have. And we'd like to see that, number one, the number of shards distributes evenly across all of the instances. And number two, that the number of active shards, in other words, today's indexes, is roughly the same as the number of CPUs on the instances that we deploy. So this complicated picture is one of the reasons that's a little difficult to scale Elasticsearch, especially in the context of multi-tenancy. When we think about how many indexes you're holding in your cluster, that really translates into how many shards you have, which translates to how many CPUs you need to support all of those different indexes in your cluster, all those different log streams. So to really understand deeply the relationship of the shards to the processing of those shards and how many index patterns you can support within your cluster, let's take a quick, deeper look at how Elasticsearch processes a write request. So let's say we'll take a single stream of data, and that stream is writing to today's index within Elasticsearch. That's represented by the black arrow with the highlighted index box. Now that index is comprised of a set of shards. In this case, it's 3 primaries, and space, because of space limitations, I only have those 3 primaries. I don't have the replicas there, but we can imagine that each of those primaries then is going to write that data. And in addition, each replica also has to write the data. So I've visualized that on the right side of the screen by highlighting both a primary and a replica for each of those shards. What this means is, as stream 1 writes data, it takes 6 shards to write every request, assuming your bulk covers every single shard, and we'll just assume that. So to process that request, I need 6 CPUs, okay? Now, when I process a query, it's a very similar story. Let's say I have stream 1, and I'm querying only today's index of stream 1. Well, that index is comprised of 3 shards and then 1 replica, or 3 total replica shards, right? My query has to go to one of either the primary or the replica for each of the shards. So I've highlighted here the 3 shards in the cluster, and I need 3 CPUs to process that request. In the write situation, I can imagine if I add in an additional stream of data, and that data also has 3 shards, I need an additional 6 CPUs. So total of 12 CPUs concurrently as those requests are coming in. For each additional stream that has additional shards in it, then I'm adding the demand on CPUs. So as I look at the need for CPUs, I have to keep in mind this picture where for a write, I have a multiplier that looks like the shards times the replicas, or for the reads, I have a multiplier that looks like the number of shards. In a read case, if I added a second index here that I was querying, or I queried a second stream concurrently, I would similarly multiply the need for shards that I need, or shards and CPUs that I need to process that. So how do I put all of that into context with the sizing of the cluster as I deploy it? I thought I'd provide some T-shirt sizing around Elasticsearch service. And specifically, if we assume a 7-day retention window, then we can look at T-shirt sizes like small, medium, large, extra large, and huge. And then looking at sizing in terms of the amount of data that we're sending per day across all of the indexes that we're retaining. And for the small one, we have 10, 500 for medium, 1 terabyte for large, 10 terabyte for extra large, 80 terabytes for huge. The storage needed is a function of how much data I'm sending per day, how that translates into an index, and then how many replicas I'm running. So if I'm sending, and how many days I'm retaining that data, right? So if I'm sending 10 gigabytes per day, then on disk, that will represent about 24 gigabytes of storage. About 10% more for the additional primary, and then I double it because I'm adding a replica. So that's 22. Then I need a little bit of overhead, which I put at about 15%, right? And thinking back to where we're alarming, that's the kind of limit of what Elasticsearch wants, is 15% overhead. Multiply that by 7 days, and I get 168 gigabytes. I have a column for the number of active shards, and what I'm trying to get at here is, if you think back to the picture of housing multiple tenants, how many tenants can I expect to put with a total 10 gigabyte a day of data sent? How many tenants can I put? And here we're in terms of how many shards do they generate. And here I'm looking at 4 50 gigabyte shards in a small use case, right? Whether that's one single log stream or potentially 2, you could get away with. 3 or 4 or more will start to overwhelm the CPU count in the cluster. My recommendation here is 2 M4 or R4 large data instances with 3 M3 medium master instances. If we move up into the medium use case, we have 500 gigabytes of data a day. And then our storage, we're going to need 8.4 terabytes to store that. I'm recommending 6 i3 2x larges. And actually, just to step back a second, for the instance recommendations, you'll see I've recommended i3 pretty much across the board. The i3 instances provide a very good cost per gigabyte number in terms of storing your data. So, and they also provide really good processing capabilities for that data. So we like the i3s quite a bit. If you can optimize a little bit on the small end and deploy smaller EBS volumes, then you may be able to cost optimize. That's why I have the M4 and the R4 for the small use case. Again, just pretty straightforward. In order to store 8.4 terabytes, you need 6 i3 2x larges. They each have 1.9 terabytes of storage. That gets me beyond what I need. And then they each have 8 processors. So that gives me a total of 48 processors. I've set the active shard here as a target of 30. And this is because, as you scale up and as you need more processing power, you also need to account for other tasks that are happening and other queries become more important in the mix. So you don't want to have a one-to-one entirely, really 40% for other tasks. So Long-winded way of saying 30 target active shards. For the large use case, again, 1 terabyte a day of storage, 17 terabytes of total storage needed, 6 i3-4X large covers that, and again, you can target 60 active shards. For the extra large, here the difference you'll see, I've adjusted the target maximum shard size. As we get up in the i3 family, the additional disk and network bandwidth gives me more capacity to deploy larger shards. So when I get into the extra large and the huge range, I can actually deploy larger shards. 10 terabytes results in 177 storage needed and 600 target shards. And not to just read the chart at you, but close to our top end would be the 80 terabyte a day, huge use case, 85 i3-16s, which would store about 1.3 terabytes of data and about 3,400 active shards. I just wanted to bring in one customer workload just to give you a feel for what people are doing and how this matters. EXPEDIA is, again, one of the large enterprise customers where DevOps is really central to their methodology. They have many different groups across EXPEDIA that are using Elasticsearch service, and they are not entirely centralizing. They're supporting many different Elasticsearch service domains. One of the things they did, and this is what we highlight in this slide, they were actually seeing some billing spikes that they didn't understand. So they took their CloudTrail data, pushed it into Elasticsearch service, and graphed it out with Kibana, and they were able to highlight and pull out the spikes in billing and figure out what was generating those spikes, and then they could remediate it. So that is all I have for today. Thank you very much for your time and attention, and look forward to seeing you on the Elasticsearch service.